Hey guys, back at it again with another video. Good to see everyone. I again am Jaden Barrett from J2 Tutoring. And today we're going to kind of continue what we've been talking about so far, with a little bit of an extra spin. Last video we talked about, how to draw polynomials in factored form with the factored form idea with the terrace, the tangent, and the regular points that you just go through. Now we're going to talk about graphing more, but it's going to be more of rational functions. Now, I'm not going to go into, what parent functions are, which is where this kind of comes from. Maybe I'll have a separate video on that. But for today, I'm just going to talk about the parts of how to draw a rational function. And you're probably like, what's a rational function? A rational function is basically when you have a fraction, okay? And you have expressions on the top and the numerator and the denominator. So an example of this, most simple example is 1 over x. Right. And this is a parent function, which is basically a basic function that a lot of teachers want you to memorize because it's very well known and it will help you draw variations of it. Like if you know 1 over x, you could do 1 over x minus 1, 1 over x minus 2, and so on. These shifts in the graph that can help you figure it out. So just for completeness, I'll show you that this is what 1 over x looks like roughly, and you could go on Desmos to even see that. But essentially it's here. Okay. That's 1 over x. Now, how do you draw these when they get really complicated? Well, there are a couple ways, but there are a few steps you want to take. So I'm going to go through the steps first, and then I'm going to do a practice problem, and then we're going to be good. So first, like always, like with everything, you want to find the x-intercepts. The intercepts are your best friend. That's what you want to figure out. You want x-intercepts and y-intercepts when you get your function, okay? The next thing is you want to figure out VAs, and I'm gonna explain what this is right now. VAs are essentially vertical asymptotes. Now, how does this work? Actually, wait, that will come later. That's not first. First is holes. There were holes first. Now, essentially, what a hole is, and this comes from the factoring part. When you factor out the numerator and the denominator. So I'll give you an example. Like if you have something like this, and then you have this, right? You could factor out the top like this, and then you could divide out the bottom. That's the idea. So when you divide this factor out, it doesn't just go away, right? It doesn't just go away. You then have to note yourself, okay, x equals 2 does not work, right? Because you can't have a number in the denominator, right? Because how you can't have anything over 0. This is undefined. Okay? So because of that, you got to note to yourself that x equals 2 does not work. So how do you denote that in the graph? Well, an open circle, essentially. This is an open circle in the graph because it shows that everything leading up to it is fine, but at this particular point, it's not equal. And we do holes first because, well, if you do vertical asymptotes first, you may call this a VA, even though it's not. It's a hole because it factors out first. So you gotta be very careful about that. You also want to simplify the expression for yourself, right? Dividing stuff out makes things easier. So that's why we do holes first or second, but like out of all the new stuff, of course, we always do intercepts. But the next thing is VA, which is a vertical asymptote, which is probably my favorite part about this. The vertical asymptote is essentially just you only look at the denominator, okay? You only look at the denominator and you're like, all right, set the denominator equal to 0. So like if I have something like this, I would set x minus 3 equal to 0. And you say, all right, x can't equal 3. And what do you do in your graph to represent this? You do a dotted line at x equals 3. Now, the reason for this is it shows that you can't be equal to this value, but you could approach it very much. And the way that these VAs work is essentially when you're approaching it, like the limit, you do negative, it either goes to negative infinity or positive infinity, depending on how the graph looks. Okay? That's essentially how this works. So that's the basics of a VA. The final portion of this is a horizontal asymptote. There's also something called an OBA, which is an oblique one, but I'm not going to go into that because that requires synthetic division. And I'll do a separate video on dividing polynomials, but that's for another day. I don't want to make this too long for you guys. But basically, it's an HA, which is you're trying to figure out the values where what equaling y doesn't work essentially, and it's not as easy as the vertical asymptote. It's not as simple because what you have to do is you got to take the limit of whatever function you have. So like as x goes to infinity, that's essentially what you're doing. And you're trying to figure out how to do that. Well, there are three rules to this basically. It's all about ratios, right? And it's about a battle. That's how I like to think of it. It's like a battle. Now, I'm not going to go into the third case because that's the oblique asymptote. That's where it comes from, but I'll go into the first two cases. So we got the first case. That's an x squared, by the way. The first case is when you have something like this. All right. When you plug, now you can't plug in infinity, but when you're doing limits, you kind of think of it that way. All right. You think, all right, I plug in infinity. We got infinity squared. I never write this on your paper ever, but I'm just doing it for the sake of the argument. We're gonna do something like this. This minus one means nothing because the infinity is gonna win out no matter what. But if you think about it, the infinity squared and the infinity squared at the top and the bottom, they're moving at the same rate, but it's doubled on the bottom. So you take its ratio. You're taking the ratio of these two, and it's 1 to 2, right? So your horizontal asymptote is at y equals a half. That's how this works. And just like the vertical one, you write it the same way, just horizontally, because all y equals constants are horizontal lines. That's the first case. The second case is when you're doing when it's well, essentially when you have something like this. So, and the third case is when the numerator wins. But it's like a war, right? If it's a tie, you take the ratio. And what I'm looking at when I say tie is the degree. The degree is your best friend. That's what we care about. We're looking at the highest degree. We don't care about the other degrees. If you have like a long quartic, which is a fourth degree polynomial, and you see these x cubes and whatever, you only care about x to the fourth because that infinity will win out against the rest of them, no matter what it is. So in this case, you're going to zero. Why? Because the bottom wins. And as the bottom gets huge, right? I'll show you an example. As the bottom gets bigger, see how I'm making the denominator bigger? We're getting smaller, right? That's the idea. So if I'm going to infinity, if I'm going to the moon on the bottom, then of course it's going to go to zero. So these are the two ideas. Now, what you do, just to show you a snippet, what you do with the third case, if you have something like this, let's say you had something like that. You got to divide it, right? You got to use, then there's a simple one, but like you got to use polynomial division. And that is a whole other technique that I will go into in a separate video, probably right after this one as like an appendage. I probably should have done it before this video. That's my fault, but I will do it afterwards. It's my next topic. But this is essentially what you would have to do if you want to get something called an oblique asymptote, which is an OBA, or an EBA, end behavior asymptote. Same idea. But these are the four components to how you draw any rational function essentially. Now, let me give you an example. If you have something like this, okay, I'm going to try to include all the parts. I don't want to make it too hard, but I'm going to try to. So, not that crazy, but we're going to start breaking it down. So, and I'll show you the Desmos after just to prove a point. So, the first thing we do, okay, is we look at intercepts. And the reason why we do that is because like it could be pretty easy to see them. Like the x-intercept, right? You're like, all right, this has to be 0. And then you're like, all right, well, when is x squared minus 4 0? Well, you factor out the top. And you could even do the whole first if you want to. That honestly wouldn't be a bad idea, especially in this case. So they're really interchangeable. It depends on what problem you have. In this case, I'd probably do the whole just because it's a little bit more obvious. and you simplify your expression. So like there you are, right? There it is. There's what I was saying, the whole. Now, very important point. In order to plot the whole, you have to plug in the -2. Okay, but you plug in the -2 into the new expression. You do not plug it into the old one because then you get 0/0, and that is an indeterminate form. And we'll get into that also in a later video. That's a cool topic, but that requires calculus, and I'm not doing that at the moment. I'm only doing pre-calc. Anyway, we'll get into calculus series 2. This is a pre-calc series. Anyway, -2, you plug this into here, right? You got the top, -2 minus 2 is -4. You go to the bottom, -2 minus 1 is -3. And then you do times -5. And then now you're at -4/15. Now, of course, this looks terrible for our graph, but for the sake of the argument, I will do it's -2, -4/15. So you go over here, you're like, all right, that's probably like there. So this is our whole. See how I did an open circle? That's essentially how you would write it. Now, of course, in school or whatever classes you're taking, they'll give you grid paper, they'll give you proper axes, but this is just for the sake of showing you, okay? That's how you do a whole. Now, once you do the whole, once you get it, you do not go back to that original form. You are now operating in this world now. You're in this box, okay? Because now you've dealt with it, you know what it looks like, you're good. Now, that was the other thing. You do have to do the wholes first in this case. Why? Because you would have thought that the x-intercept was also -2, which would have been a problem because it's not, because it's a whole. It's an indeterminate form, so it doesn't count as an x-intercept. You know what is our x-intercept? 2. 2 is our x-intercept. That will get us 0. That will get us 2, 0. So we go back up here and we say, okay, we have our 1 x-intercept. So that's handled. Okay. The other thing is you got to find the y-intercept now. Now that's easier to find. Um, because you just plug in 0 for x and you're like, all right, well, -1 times -3. It looks like we're at -2/3. Okay. So then you're like, okay, -2/3. You have this here, you go here, you go like, I don't know, here would be -2/3, I guess. You can call that -2/3. There's no scale. But you get my point. We have our intercepts. And why does this matter? Because this will help us figure out the direction of our graph. And the asymptotes will do the same thing. The vertical asymptotes are insanely quick. You just got to remember that you're only looking at the denominator. Screw the numerator, it doesn't matter. Now, here's what's cool. You realize that, okay, x equals 1, x equals 3. Why is that true? Because if I plug these into the bottom, I get 0. Do we agree? We have 1 minus 1 times -2. That will get us 0, etc. If I did the same thing. Remember, that's what a VA is. So 1 and 3, right? 1 and 3 are what we were looking at. Now, why is this really cool? Why is this really cool? Well, because you're going to see that our graph is going to get really like, how do I put this? It's going to get really tight. Okay, it's gonna get tight because you're now here. You're living in these confines, right? And the last piece of the puzzle is the horizontal asymptote to really box in your graph. Now, this is the hardest part for a lot of people, but if you're smart about it, it's not so bad. Because I mean, I know because I set this up. With this problem, it's 0. And how do I know that? Well, I have a linear up here, right? Linear just means that the number one degree is 1. And I have a quadratic down here. Why? Because I have two factors. Remember, the quadratic has two roots. So you don't even have to multiply this out. I know the lead degree is going to be quadratic no matter what. It's going to be a 2. So what's bigger, 2 or 1? 2, right? So the bottom is going to win the war when you put the infinity on the thing. And why do we do to infinity? Because remember, these asymptotes are going to infinity. That's the entire idea of them. So that means that we have an asymptote cutting straight through the middle. Now, this is very interesting about horizontal asymptotes. I didn't bring this up till now because I wanted a really cool example of this. You can cross horizontal asymptotes, but you cannot cross vertical asymptotes. It's very important. You will never cross a vertical asymptote in your life. That will never happen. That's why they're really powerful because it can help you figure out where you're going. Okay, it's very cool. Now, you're probably like, well, where am I going? How do I even draw this? Well, for one, you have to pass through every single intercept and every single point that you've drawn already. Part of what you could do is you can start plugging in points, right? Like I already know, like I got to figure out if this is going down or up. Okay. It's hard to tell. It's hard to tell, but you're gonna have to cross the horizontal asymptote somewhere. Like I know that this happens because we have to pass through that hole. Not really, that's why I left a space. You have to go in that direction. You got to pass through the whatever you call it, the y-intercept. But here, I know I have to pass through my vertical asymptote. Sorry, my horizontal asymptote. But here's something that you must realize is that the second you pass through it, you just it flattens out. It does not go any higher, it does not get any lower. Remember, you're going through it. You're just going right above it. It's coasting, you can think of. Now, how do you figure this out? You have to plug in values. So that's kind of what's annoying about this is you have to plug in values into here to figure out what's going on. So like if I plugged in 100, okay, this is gonna be a very it's gonna be a positive number, which is good to know because that means that we're gonna be above it when we get bigger. That's the important part. So this is gonna be like here. And you know what's interesting? Let me make this better. What's interesting about this and why I find this really cool is like I just said that it mellows out, right? If I plugged in 100, right? Just for sanity's sake. If I plug in 100, notice how close we get. We get 98. Remember, we're looking at the new one, not the original problem. 98 over 99 times 97. Dude, that is huge. That bottom is huge, which means our fraction is so small. And what happens when a fraction is really small? It's really dangerously close to zero, right? But I know it's positive. That's how I know that it's going to mellow out above the line and not below it. That's the idea. Okay? But it had to be coming in from the bottom. Okay? Or maybe not. It might not have actually. I might be wrong about that. So we have to check something like 1 or even we have to check well, where's our vertical? Our vertical asymptote is at 1, right? So we need to check something like 1.5 in between to really understand what's going on because it's a 2. So this is where it gets dicey, right? Like we know it's a negative up here. This is where it gets tough because you have to figure out what direction it's going in. And there's not really any other science to this. This is going to be a positive number though, because we're at zero point 0.5 and then it doesn't really matter. It's negative. That's the whole point because 1.5 minus 3. Well, negative 1.5. So, well, no, it's not actually, I'm sorry. The bottom's negative, yeah. Which means the whole thing's positive because the top's negative. So because of that, I know that it had to be coming from up here or like this. This is what it's supposed to look like. Okay. It now it doesn't necessarily cross two, but it's getting like it's close. So it crosses the line, but then it comes right back up. That's the idea. Now on this side, you got to realize that you're coming down, okay? Because you have to hit this y-intercept, and you can't cross this vertical asymptote, so it must be coming down. Now, this hole, what I would do is I would plug in negative 2.5 to figure out if we're above the line or below the line. Because remember, you can cross a horizontal asymptote, but we don't have a point there. So it probably won't be positive, but it's not a bad idea to check. Negative 2.5 here, that'll be negative 4.5. So that's negative, negative, negative. Everything's negative, which means we are a negative number, which is what I said before. Because remember, it's always good to check, always good to be careful. But because we didn't have a point there on the horizontal asymptote that was like, oh my God, we're gonna cross the horizontal asymptote, it probably won't. But it's not a bad idea to check. Okay. Now I drew this kind of poorly because I was just showing you what direction it goes. But technically, this is supposed to dip down. Now I know I have that touching, but just know like it gets insanely close, but it's not crossing. Okay, so it's like that. It's like a negative it's an upside down parabola. And then you try to figure out, well, what's going on the left side. So if I put like negative 100, you got to figure out what the end behavior is. So everything's negative and it's going to end up being a negative number. So you're just dipping down. It's just going to get really close like this. It's never positive. Okay? That's what this graph looks like. So it's kind of crazy, but with all of these parts, you're able to figure out what's actually happening, which is the beautiful thing. Okay? I know that's a messy picture and I really apologize, but I do want to show you really quickly. Let me just write down this question on my paper. I do want to show you what this looks like. It's not going to be perfect because I just did a sketch, But just for your own sanity, I want you to see what this looks like on when I share my screen, because I think that is really valuable. Let me X out of this really fast. I think that could be really valuable. So that's what I want to do. So I'm just going to show you what's going on. So if you see, I had this from our last lesson actually, but if you see what happens here, because Desmos is beautiful. I do love Desmos, but if you do this, look at this. So you have this. Oh, I should put a y equals, my fault. That. And then you're like, okay, x squared minus 4 over, and then you do x minus 1. It's gonna come into form. It's gonna come into focus in a second. I just want to type it in, but it's also gonna be embarrassing if I got this wrong, but I don't think I did. All right, so where's the oh, here it is. Okay, so do you notice? So they don't when they're drawing it in Desmos, they don't fully show you like all of the asymptotes, like with the dotted lines. You just do that when you're writing it yourself by hand. But if you notice, like, if you look over here, and I was right though. Like, this is here. See, this is the asymptote that we got. That was negative 2/3. Sorry, the intercept. This is here, right? It dips like we had before. We have this hugging the top over here. But notice it does cross here. Now, my mistake was that it's not always perfect, but your vertical asymptote is here, um, as well, which is why this is so great, right? I mean, we basically got it for the most part. I think my mistake was that I had a vertical asymptote at 3, but the point was at 2, not at 4. I miswrote it because my whiteboard was really tight. But my point is, notice how like we've figured this out with the 4 parts, right? And the only case that I didn't cover was the OBA because I don't want to make this video too long and it takes a while to do this. But like you could really do this and just check it with Desmos. So it's a very powerful tool. Okay, we don't even know what this we had no idea what this looked like before all this. Like how are we supposed to figure that out? Didn't even use a parent function. You used nothing. So yeah, that's essentially how this works. I just wanted you guys to see that because I think it's pretty cool and I think it's awesome. But yeah, that's essentially how you draw rational functions at its most basic level. If you have any questions, please leave them in the comments. And if you want to learn more about it in more detail, then join us at j2tutoring.com. We'll get you a lesson. Thank you so much and have a great night, everyone.